Hi everybody, it's Professor Marinos again, and today we're going to continue our discussion of thermodynamics by discussing one of the most useful properties that you can measure in a chemical system. That is the state of enthalpy. Now, by the end of this video, you'll be able to define enthalpy in terms of heat. What is this funny sounding word? Who knows? And secondly, you'll be able to predict whether a reaction gives off heat or consumes heat based on enthalpy calculations. So let's launch into it. Okay, so we're going to discuss enthalpy. Enthalpy is denoted by the letter capital H. And what enthalpy is essentially all the energy that would be required to create a system out of nothingness. So to impart energy into its particles and to give the space for the system to exist in. And so enthalpy is comprised of the internal energy, that's the energy that goes into the molecules and the bonds, in the vibration of those molecules, plus the product of pressure and volume, which is essentially the amount of work required to push the surroundings out of the way such that the system can occupy a physical space. You can picture this as the amount of work required that the gas performs pressing against the walls of a balloon. And again, this is a product of pressure and volume. So you'll recall from our lecture on the laws of thermodynamics that internal energy of a system is unknown. And therefore, H is also unknown. Enthalpy is also unknown. So what use is this? Well, you'll recall from the previous lecture that although we can't know U directly, we can't know internal energy directly, we can measure changes in the amount of internal energy in a system. And the formula that we gave for that is delta U equals the amount of heat applied or removed from a system, Q, plus the amount of work that the system does on its surroundings, or the amount of work that the surroundings do on its system. And so similarly, we can rephrase H as delta H, the change in enthalpy, as the change in U plus PV. Well, okay, so this is all fine and good, but what use is this? Well, we can make a few simplifying assumptions that make this concept of enthalpy very useful for chemistry. The first assumption that we're going to make is that the pressure of the system that we're working with is constant. And this is a pretty good assumption on the face of the Earth. Pressure doesn't vary all that much, very minusculely compared to other properties of the system. And this allows us to rewrite the equation as delta H equals delta U plus P delta V. Okay, so let me start this over, start a new sheet. I'll just rewrite this equation that I just finished up with. And now you'll recall that we did have a expression for the amount delta U, so we can trade that expression in for that term, and that is the amount of heat into or out of a system plus the amount of work done to a system or done by a system equals delta U. And so we just plug that in, and we're left with heat plus work plus P delta V is equal to the change in enthalpy. So where does this get us now? We need to make one more simplifying assumption. And the second simplifying assumption that we're going to make is that work is only pressure volume work. Now, pressure volume work is a change in volume driven by a difference in pressure. And if we make this assumption, I don't want to get too much into the details about why we're going to make this assumption, but if we do make this assumption, we can express W as negative P delta V. And so, if we rewrite our equation for enthalpy again, we're left with a dramatically simplified equation, which is simply that delta H equals Q minus P delta V plus P delta V, which of course those cancel out. And so we're left with the change in enthalpy equaling the amount of heat coming into or out of the system. And that is a very useful definition, and we can see why in just a second. So, this is a useful equation because heat is an eminently measurable property. If you have a system that you know a process is occurring in, and you're wondering how that's changing the internal energy of that system, then what you can do is you can take the system and put it in a well-insulated box called a calorimeter, and then measure the temperature of the surroundings. And depending on which way the temperature changes, you can back out how much energy must have entered the system or left the system in order for the process to occur. Now, say in this system that you're considering only a chemical reaction is occurring. Then what you have is what we call the heat of reaction, or the enthalpy of reaction, delta H sub R, and this is measured in joules per mole of product. And what the heat of reaction tells us is how much heat is drawn into the system in order to supply energy to create the chemical bonds in the product, or how much heat is released from the system as the chemical bonds are broken from the reactants and reconfigured into the bonds that form the products. So if the products contain more energy in their chemical bonds, then the heat of reaction is positive. The internal energy of the system is increasing, and so it's drawing heat from its environment. And we call this an endothermic reaction. If the products contain less energy in their bonds than the reactants, though, then the internal energy of the system will decrease as the reaction progresses, and so heat will escape into the surroundings. And this we call an exothermic process. So if the heat of reaction is less than 0, it's an exothermic process. If the heat of reaction is greater than 0, it's an endothermic process. So if we have a reaction occurring in a system, we've defined what we mean by the enthalpy of reaction, delta H sub R, or here I wrote delta H sub reaction. And if we do this at a condition of 1 bar pressure, we'll have what we'll call the standard enthalpy of reaction. And this is just a way to standardize the numbers that you can look up in tables. So if we don't have a calorimeter around with us, though, how can we determine what the standard enthalpy of a reaction will be? How can we determine if this reaction will be endothermic or exothermic? If this energy output in joules per mole or kilojoules per mole is going to be positive or negative? Well, if you take the change in enthalpy that's caused by a chemical reaction, that change in enthalpy is the difference between the enthalpy of the products and the enthalpy of the reactants. But now you recall that the enthalpy of both the products and the reactants in their absolute form are unknowable. So where does this really get us? Well, we can't know these quantities directly, but the fact that we have a balanced chemical equation means that we have the same amount of each element starting off as reactants that we do have as products. So the equation is balanced, and so what this does is it allows us to define a useful quantity called the standard enthalpy of formation. And what this is simply the change in enthalpy that occurs to make each of the products and each of the reactants from their elements. So we write this delta H sub F, and this is something that can be experimentally measured just by starting with the elements that compose all of your products and reactants and measuring the enthalpy changes that occur as you create each product and each reactant in your equation. So just to take an example, like water, this enthalpy of formation of water is measured by combining hydrogen and oxygen in an atmosphere and measuring the change in enthalpy that occurs as this hydrogen and oxygen is transformed into H2O. So the enthalpy of formation of elements is always defined in terms of the most stable form of that element. So for sodium, it's elemental sodium. For oxygen, it's diatomic oxygen. And for iron, it's elemental metallic iron. And of course, the enthalpy of formation for elements is always 0, because the change in enthalpy to go from an element to that same element is 0. And the enthalpy of formation for almost every compound on the face of the Earth has already been measured by your local hardworking chemist, slaving away in front of her calorimeter. So you can look up these values in tables and use them for your thermodynamic calculations. But now, how do we go from the enthalpies of formation of all of the reactants and products in a chemical reaction to determining the enthalpy of reaction, whether or not a reaction will be endothermic or exothermic? Well, you'll recall that the enthalpy of reaction is equal to the enthalpy of the products minus the enthalpy of the reactants. And this enthalpy of formation has now given us a useful baseline
that we can use to determine the enthalpy of reaction. And so we can calculate the enthalpy of reaction simply as the sum of the stoichiometric coefficients, n, of the products. So like if a reaction produces 3H2O, then n is 3, multiplied by the enthalpy of formation of all those products. So you multiply the stoichiometric coefficient times the enthalpy of formation for all the products, and you sum this up. And then you subtract from that amount the exact same thing done to the reactants. So the stoichiometric coefficients of the reactants multiplied by the enthalpies of formation of the reactants. And this gives you the heat of reaction. And again, this enthalpy of reaction is going to be expressed in kilojoules per mole or joules per mole. Okay, now that you know how to calculate the enthalpy of reaction to determine if a reaction is going to release heat into the surroundings or take up heat, whether it's going to be exothermic or endothermic, let's try an example problem. This example is the respiration of glucose, one that is very important for all life on Earth. And in this equation, written below, we have glucose, C6H12O6, plus 6 oxygens yields 6 carbon dioxides plus 6 waters. And it provided the enthalpies of formation for both the products and the reactants for you, so you don't have to go look them up. Let's determine if the reaction is going to be endothermic or exothermic. What is the enthalpy of reaction for the respiration of glucose? Okay, so I've written the chemical formula above, as well as the formula for the enthalpy of reaction. Now let's start trying to solve this equation, starting with the products. So let's look at our products. We have 6 CO2s produced times negative 393.5 kilojoules per mole enthalpy of formation for carbon dioxide, and 6 waters produced with an enthalpy of formation of negative 285.8. Let's move on to the reactants. In the reactants, we have 6 oxygens times an enthalpy of formation of 0 for each oxygen. And then we have 1 glucose times an enthalpy of formation of negative 1,273.1 per mole of glucose. Now we can do some math. And we get a final result that the enthalpy of reaction for the respiration of glucose is negative 2,802.7 kilojoules per mole. Now, kilojoules per mole of what? Well, it's per mole of glucose, because glucose was the only reactant in the equation that had a stoichiometric coefficient of 1. If we wanted to figure this out for a mole of any other constituent, we would just divide by 6 and arrive at the enthalpy of reaction for 1 mole of any of those things. So this determines that the enthalpy of reaction for the respiration of glucose is exothermic. It is a heat-giving off process, which is concordant with what we know about biology. We can burn glucose in our body to create energy in our body.
Now, there's been a good bit of math done in this lesson, so I just want to reiterate the take-home points from this lecture in terms of equations. The first equation is very simple. The change in enthalpy of a system is simply equal to the heat flux into or out of that system, denoted by letter Q. And this is very useful because this makes enthalpy a measurable quantity in relative terms. We can always measure the change in enthalpy using a calorimeter. The second equation that I want you to take home is the equation for the enthalpy of reaction for a chemical reaction, expressed in kilojoules per mole and denoted by delta H0 sub R. Now, recall this is the sum of the stoichiometric coefficients of all the products multiplied by their respective enthalpies of formation, minus the sum of the stoichiometric coefficients of the reactants multiplied by the reactants' enthalpies of formation. So take both these formulas and put them in your pockets, because we are going to run them ragged over the next few days. Okay, so in this lecture we discussed enthalpy and figured out how we could use enthalpy to determine if a chemical reaction will give off heat or take in heat from its surroundings. And I'm going to let you sit and get a little bit more comfortable with this concept of enthalpy and do a few calculations. But after you feel comfortable with it, please return, because we're going to move on to Gibbs free energy, which is even more thrilling of a topic than enthalpy is. So if you were just thrilled by this lecture, hold on to the seat of your pants, because things are about to get wild.